the third session of day second. So more people are joining. We will start very soon. So as we discussed in the first lecture today, that in the afternoon we will be discussing finite difference method. So let me share the screen and let us quickly uh, recap what we did in the last lecture. Yes, so right, yeah. So I hope my screen is visible and yes. So in the first lecture, what we discussed that we need to develop or extend Black-Scholes model. The reason is because there are certain limitations in the Black-Scholes model. But at the same time, we observed that if you extend Black-Scholes model, then it is difficult to solve those to find the closed form solution of those. Right. So that clearly says that now we need to go for numerical methods. Okay, so I just want to have, I mean, if you have any queries still here. So what we did in the last lecture, we understood some basic definitions about options, and then we discussed some research problems. What are the research problems? So one of those research problems is this numerical methods for solving option pricing problems. Then we realized that what is the really need of this numerical methods for option pricing problems. One of those method is finite difference method, and then we read this Black-Scholes PD. After that, we read this solution of Black-Scholes PD. So it is easy, right? We'll do it in MATLAB. That once you know all these parameters, right, you'll simply get the option price. So we'll be doing this in MATLAB. But before that, we'll go for numerical methods, right? So someone asked that, can you suggest one book? So I suggested one book for this computational methods for option pricing. So this book is fantastic. You can go through it. And today, now in the second lecture, we are going for finite difference method. So we will start finite difference method for heat equation. The simple, some of you can ask that why for heat equation it is not option price in PD. Yes, I agree. But as I said that heat equation is quite easy to understand. So better we should go for heat equation. And once we get the concept, once we understand the concept, we can extend it for Black-Scholes equation or many other equations. So this is lecture 3, and as some of you asked in the last lecture, so I'm just giving the book name prior, right? So the book reference book you can see. So this is the reference book for finite difference method, right? This is the reference book for finite difference method. So the book you can see numerical partial differential equation, and finite difference method. This is the title. So this very good book on finite difference method, either from course wise, if you want to read finite difference method for your project, or if you want to read finite difference method for research, it is good for all the purpose, right? Author is J.W. Thomas. This is title. Author is J.W. Thomas, right? And Publisher is Spencer. Right. So whatever we are going to discuss in this lecture, we will be following this book. Those who are interested, they can go look at this book and they can simply understand the concepts in more detail. So with the assumption that audio and video is perfectly fine for you, if not, please do let me know, right? So the very first thing which we are going to do, heat equation. So I'm starting from scratch. Some of you might feel that it is very basic, but yes, I'm starting from scratch, and once the fundamentals are established, you can extend this to any partial differential equation. Okay, so the very first question, we'll take one heat equation. So ut equals to uxx. I'm not going in much detail about equation. So because our purpose is not to solve the heat equation, our purpose is to solve the black source PD, right? But even more than that, our purpose is to understand a numerical method, right, which is applicable for all type of partial differential equations, right? So sine pi x, this is the initial condition, and u is ut at 0 is 0 and equals to ut at 1, and exact, let me write it, then we will discuss one by one everything, right? Exact solution u of tx equals to e to the power minus pi square t sine pi x. So this is the heat equation we have taken. How many of you, I mean, it's just a small question, how many of you have read earlier this heat equation? Anyone? Okay, so yeah, most of you, I mean, no, okay, fine, then that's good actually. So you have not read, okay, fine. So it's a simple partial differential equation. Why it is a partial differential equation? Because it is, there are two independent variables, t and x, right? And u is basically here unknown variable, so you have to find this variable u, and ut is basically partial derivative with respect to t, xx, that is second partial derivative with respect to x, basically twice differential, right? So I think Sarthak, that is okay. Ut and uxx you understood. And what about this? Let me take it. So this is your main PDE, right? This is your main PDE. What about this equation? This is nothing but initial condition, right? Why it is called initial condition? In a simpler way, that at time t equals to 0, you know the value of u, right? You know the value of u, t equals to 0, right? And for all x, t is 0, but x is anything, right? Anything from 0 to 1, the value is sine pi x. And what is this called? Boundary conditions, right? So here, and t, you can take t is from greater than 0, and you can find the solution at any t. So what about this exact solution? What does it mean? Let us try to understand. Right. So first of all, this solution satisfies the original equation. Is it? Can anyone verify quickly? Can anyone quickly verify that yes, this exact solution satisfies the PDE, right? So it should satisfy, isn't it? right? So let us check. So exact solution satisfies. Can anyone confirm quickly the
Yes, sir,
PDE?
it is satisfying, sir.
Yes, it is satisfying. Thank you. So for those it is not clear, so let us quickly see, right? It is not a very big deal. So we will try to understand the PD also, and then we will try to understand how do we solve it, right? So what will be UT? UT means del U by del T, right? What will be its value? E to the power minus pi square T into minus pi square into sine pi x. Fine. And what would be del u by del x? That is ux. This will be nothing but e to the power minus pi square t into pi cos pi x. And once again, if you differentiate del 2u by del x2, that is uxx, that would be nothing but minus pi square e to the power minus pi square t sine pi x. I hope it is clear to everyone. So these two are equal, so it is satisfying, right? So the solution means you have to find a function, right, which satisfies the PD. But my next question is, does it satisfy the initial condition also? Everyone, from here what we can see, yes, exact solution satisfies PD. Yes. Now, does it satisfy initial condition also? So what is our initial condition? Initial condition, right? That is sine pi x. And what is your exact solution? Ux comma t, that is e to the power minus pi square t into sine pi x. Now you put simply t equals to 0. What you'll get? That is yes. This
Sine pi x.
sine pi x. Fantastic. So till here also I think it is okay, everyone.
Yes, sir.
Right? Yes. So now tell me whether it satisfies boundary condition also. Boundary condition, x is from 0 to 1. X is from 0 to 1. So put at x equals to 0, you put x equals to 0. So if you put x equals to 0, that is ut comma 0, what you will get? 0, because sine 0 is 0. And if you put t x equals to 1, sine pi is also 0. So it is satisfying boundary conditions also. Everyone comfortable till here? Right? So we understood that what actually I was trying, those who are not clear, those who are from undergraduate maybe. So I was trying to explain that yes, solution means it satisfies the PD, right? And we have checked it. Okay. Now, what does this solution represents? Let us try to understand what it says. Uh, okay, Aditya, Sarthak, everyone, right? It's fine. So now let us try to understand that suppose we know uxt is the solution. Sorry, I'm writing. Okay, fine, it's okay. Either you write utx or uxt, it's okay. E to the power minus pi square t sine pi x. Okay. Now, if I want to find the value of u at 0.5 comma 0.5, what do I need to do? I can simply calculate using calculator 0.5 comma 0.5, that is e to the power minus pi square into 0.5, and this is sine pi by 2, right? We can simply calculate this value. So what I wanted to convey from this, that yes, for any value of x and t in the range, x is from 0 to 1, please be clear, right? It's not like anywhere, and t is greater than 0. So for any value of x and t, we can find the value of u. So this is the advantage of a closed form solution or analytical solution. or exact solution. Agree, everyone? So if we have an equation, we have its exact solution, we are happy. The reason is simple, that for any value of x and t, we can find its value. So now let us, I'll just associate here so with the Black-Scholes equation, because our prime objective is that. So we know the value for Black-Scholes formula, right? We know Black-Scholes formula, right? What it was, Vst equals to S n d1 minus k to the power minus rt minus t and d2, right? So if we know this from this exact formula, for any s, for any t, we can find the value of v. Yeah, this much is clear to each of us, that yes, but if there is no exact solution, suppose you don't have exact solution, then how will you find this value? So for heat equation, maybe, right? For heat equation, right? Try to understand. If we don't have, if no exact solution, how to find u at 0.5 comma 0. Question is clear? The first question is that how to find. That means you have to solve numerically, but how to find 0.5 comma 0.5? Right? Or any 0.4 comma 0.3, 0.2 comma 0.1, whatever, how you will find. Right? So suppose I want the value of u at 0.5 comma 0.5. So what I will do for this heat equation, and this is what we are going to do with finite difference methods. So let us try to understand via a figure first, right? So what we are going to do, and first we will understand figure, and then we will explain theoretically, right? So what we will do, please try to understand. We will take, and u is a function of x and t. So we take x on this side and t on this side. Right? T is on this side. Okay. Now this equation is defined for x 0 to 1. Okay. And t also we take, suppose 0 to 1. That okay. We don't want more than t value more than 1. We want ux 0 0.5, 0 0.7, 0 0.9, but t also, suppose we want t equals to 1. It's not necessary, but yes, you can take it like this. T equals to 1. Now, what we will do in finite difference, we will divide this in several parts. So suppose we divided it in 10 parts, right? 10 intervals. We divided from 0 to 1 in 10 intervals, and in the same way we divided in, right? We divided t also in 10 intervals. Okay. Now it will be, I mean, if you take 10, then it might be a bit complicated. It's okay, right? So what we take, at each step we take it as delta x. What is this? Delta x. So tell me, what will be the value of delta x? What will be the value of delta x?
1
0.1.
by 10.
Fantastic. Thank you. Yes, 1 by 10. This is 1 by 10. And in the same way, what will be the value of delta t? Again,
Same, sir.
1 by 10. But is it always necessary to take equal number of delta x, delta t? No. right? It is not necessary at all. I have taken here just for simplicity, so no need to take it, right? Okay. Now, so tell me, this is 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. So this is 0 0.5, and here also this is 0 0.5. So technically what you want, you want the value of u at this point. This is what? Agree, everyone? You want the value of u at this point, right? So now what we will do, this is what we are going to do. And what is your initial condition? Tell me, what is your, in this figure? So we'll try to make this figure in the way that, yes, just a minute, right? Right. And then in the way, right? And then you can draw this like grid, isn't it? So what we are going to do with finite difference, it is seems complicated. We will take only 3, right? Then it will be more clear. Don't worry. So, but yes, so we have discretized x and t. It's not necessary that we need to take 10 points. Please be clear. It is not necessary that we need to take only 10 points. It is not necessary that we need to take delta t, delta x equal. It is just, it is your wish. Okay? It is your wish. Now, how to solve it? So please understand that what is initial condition and what is boundary condition. So this value, this is called initial condition. What it is? Initial condition. And these two, what? This one and this one. Why? Why these are boundary conditions?
Endpoint, sir.
Boundary conditions. Please try to understand why it is initial condition, because t is 0 here, right? As t is 0, right? T is 0 here. So what was our initial condition? Initial condition t at 0. You see here, t is 0. And what are boundary conditions? T is anything but once x is 0, which is this one. Yeah, this is x equals to 0 and this is x equals to 1. So in this figure, everyone is comfortable that where are the boundary conditions and where are the initial conditions. Now please let me know that, yes, we already know boundary condition, initial condition, so we don't need to find the solution at these 3 points. It is already given to us, right? It is already given to us. Okay. And we can take 10 points, 20 points, 1000 points, 10,000 points, even 3 points, 5 points. Okay. So where we need to find the solution? We need to find the solution at these points. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then this point. Please try to understand. I'll explain crystal clearly. Please wait, right? So at these points, we will find the solution. So what is this point? This is technically u 0.1 comma 0.1. Is it clear to each and everyone? Aditya, right? So, Sarthak, everyone? Yes, Pooja, thank you. What will be this point? Can you tell? U at if you take as a U as a x comma t, right? Right? That U 0 is 0.9, x is 0.9 and t is 0.2. So fine. We got your 0.1, whatever point. So suppose I get the solution at these points, and then whatever point you'll ask me, I'll give you the solution. Now there are two questions, right? One, if I want the solution at 0.85 and 0.25, what should we do? See,
Sir, we can
0.9
make
and
some more
0.2 I'm
partitions
getting.
also.
Exactly. Thank you. Thank you so much. So this is the simplest answer, right? You have to refine your grid so that you get one grid point here. So these are called grid points. These are called grid points, right? So you have to refine your grid in such a way that there will also be a grid point. So grid point is what? How you are getting grid points? Grid points is basically intersection of x and t, isn't it? You are drawing a line on x and t, and whatever the intersection, right? That is grid point. Here one intersection, then here one intersection, then here one intersection, here one intersection. Everyone comfortable? So that means whatever point you will tell me, I can obtain the solution. Only thing is I need to take as much as point between 0 and 1. Agree, I think, right? So whatever point you will tell me, you'll tell u at 0.001 and t at 0.001. Only thing is I have to take 10,000 points. It will be 0.001 and 0.00. So we all agree. So it's fine. And this is what the numerical solution is. So what we are going to do, we are going to find numerically using finite difference method these solutions. Okay. So what we are going to do, everyone, let me just write a few things. Just a minute.
Sir, one question, sir.
Yeah, please, please.
Sir, then there will be infinite number of points in this particular grid points if we go just go on deep inside. So there will be more points, I mean, more grid points coming, right, sir?
Yes, if you increase more and more, the grid points will increase, but that will increase your computation also. So we have to be very careful that how much grid points we should take.
Okay,
Numerically, when we'll solve it, I'll show you that how your computation is increased. Okay, so
yes, sir.
suppose we represent it. I hope it's clear to you. Is it clear to you?
Yes, sir. Yes, sir.
Yeah, okay, fine. So what we are representing, how we represent our grid, let me represent some notation here. So please do not be confused if you are some feeling somewhere. So we are representing this each grid point in x direction by xk, and xk is k times delta x. So tell me, and where k is 0, 1, 2, and so on, 10. Agree? So you can simply see, let me change the color so that you can even more understand clearly. So this is basically x1, right? This is x2, this is x3, and so on. And what is x3? X3 is 3 times delta x, because this is delta x, this is delta x, and this is delta x. Right. So here you see x3 is what? 3 times delta x. X9 is what? 9 times delta x. Everyone comfortable? Right? And in the same way, here also t variable also we can define, right? So technically, what we need to, how we are going to solve it, right? Good. So this is the now the question, that how we are going to solve it, right? So I'm not sure whether you people are comfortable or not, but let me try. So we, using Taylor series expansion, we can simply write this del u by del t. This is nothing but u at, like, okay, let me define a notation first, otherwise you may get confused. Just a minute, okay, just a minute, otherwise so those are very, having not having any knowledge, still I'll try to explain them. So we, so u n k, this is representing u, value of u at the point k delta x comma n delta t. What does it mean? That if I want to find the solution at this point, this blue point, this C, okay, let me take another color, this green one, this dark green. So how, and this was what, 0.5 comma 0.5. So how we should represent it? We should represent it u5 5. Is it clear to everyone? Right? u5 5, because this is in x also it is at fifth place, and in t also it is at fifth place, right? So right, so what, this is that notation which we need to keep in mind. Now it will be clear, right? Don't get panic if you are not getting, just allow me for some more minute. So we all know that our equation is ut equals to uxx, and we will discretize it, right? We will discretize it using finite difference approximations. What is finite difference approximations? That is important to know, right? So we know that ut at xt, this can be written as u of x comma t plus delta t minus u of x comma t upon delta t as limit delta t tends to 0. How many of you recall this? This is simple class 12, right? Derivative, partial derivative of function. This is nothing but partial definition of partial derivatives from class 12. I hope you can recall. Those who cannot, they can simply just by looking at any book on class 12, right? So partial definition of partial derivative, that ut you can define from this, and from here only, if you expand this u by Taylor series expansion, you can simply obtain that ut at any k delta x and n delta t, you can write like u n plus 1 k minus u k n upon delta t. So this I'll take up some time to explain you again, so that you should not have any confusion, right? So this can be written u k n plus 1 minus u k n. Why? Because you just put in the above, in this you put x in delta x in place of x and delta t in place of t. So what it would be? This would be k delta t, right? Okay, let me take you. You just replace x by k delta x and t by n delta t. So tell me, this one you are going to get this, right? UKN, because UKN is what you see here. Okay, uk delta x and delta t is nothing but ukn, and this one will become this. Why? Because here n plus 1, why it would be n plus 1? Because here it is t plus delta t, right? One more step. So suppose you want to find uk n plus 1, that means what? uk delta x comma n delta t plus delta t. That means one more step, or you can write it in a way uk delta x comma n plus 1 delta t. I hope I'm clear enough that ut you can discretize using this equation. Ut you can discretize using this equation. So we started with heat equation, right? Let me again recap quickly. We started with heat equation. We took one example where there is a initial condition given, there is a boundary condition given, there is exact solution given. Why we are doing this question? Because we will try to figure out the numerical solution of this heat equation by a finite difference method, and then we will compare our numerical solution with exact solution, and we will see what is the error, right? And then we saw some beautiful things that exact solution satisfies PD, initial condition, and boundary conditions. And then what we realized that we started to understand that how finite difference method is applied to heat equation. So first we saw some motivation, that suppose we want to find 0.5 comma 0.5, or we want to find 0 comma 9 comma 0.2. So we need to make this grid, but it seems very complicated. That how much? Okay, some of you asked that sir, it will be too lengthy grid. Then how will we do it? Actually, we don't do it. It is done by MATLAB. I'll show you the codes, right? It is automatically done by MATLAB. So you have to just enter whether you want to take 10 number of points, or you want to take 20 number of points, or you want to take 100 number of points. MATLAB automatically does it. Clear enough? So how do we do it? We proceeded with this notation that we take ukn equals to uk delta x and delta t. So ut k delta x and delta t. That means the differentiation with respect to t, that can be written by this. And it is not equal, it is approximation, right? Because there will be some more terms, some will come. Please understand, right? Some more terms will come. And in the similar way, your double. So what we are going to do, please try to understand. This is our PD. We want to put its discrete approximations in place of ut also, in place of uxx also, and then we will try to solve. Got my point? What we are going to do, we are trying to put in place of ut also and in place of uxx also, and then we will try to solve it. Okay, so let us try to understand. Don't worry, right? So let me just write uxx also, right? Uxx at I mean kn, right? At k at n. So this will be what? Again, u at kn plus, just 1 minute. If someone is not comfortable in this approximations, I'll explain again in detail, but please wait for some time. uk plus 1 n minus 2 ukn plus uk minus 1 n upon delta x square. So this is the approximation of first derivative with respect to time, and this is the approximation of second derivative of u with respect to. So this is the derivative with respect to t, time, and here the derivative with respect to x. Very well. Right. So I request that please assume as of now this equation is star and double star. If it is not clear to you, of course I'll make it clear. Don't worry. First, we will try to understand the how this finite difference method gives us the solution. Then we will go for implementation in MATLAB, because without knowing theoretically going for implementation is not a good idea. So what is the idea? We saw that we discretize our x domain, we discretize our time domain, right? Then at any point, why we are calling it u5 comma 5? I hope it is clear to each and everyone, because this is the point. What? This is 5 delta x, and this is also 5 delta t, and this point is intersection of 5 delta x and 5 delta t. I hope it's clear to everyone, right? So now the idea is that we now write these two equations. We know. So what was the purpose? That for PDE we are going to discretize it using finite difference approximation, and these two are called finite difference approximations for first and second derivatives. Equation star and equation double star, these are called the finite difference approximation of first derivative and second derivative. Agree? So what we did now, let me complete it. If not, it is not clear to you, I'll come back. So let us define a smaller grid so that I can tell you by forming the equation. So this is 1, this is 0, this is 1. We are dividing it only in like 4 points. Okay, here also it is maybe 3 points. Maybe again 4 points we can take, it will be easier, right? So this is 0 0.25, 0 0.5, 0 0.75 and 1, and this is again 0 0.25, 0 0.5, 0 0.75 and 1. Okay, now what the equation we have, please see from above. What the discrete form of PD we have? Discrete form of PD we have ukn plus 1 minus ukn upon delta t equals to uk plus 1n minus 2ukn plus uk minus 1n upon delta x square. See, lot many things are pending still. Okay, so better we take it as v, because it is approximation. Please be clear, right? It is approximation. These are not equal. Some error is there, right? So let me rewrite it. Just 1 minute, okay? Because it is a bit confusing, but if you pay attention for next 10 to 15 minutes, I'm 100% sure that it will be clear to you, right? No need to worry. So right, so the idea is simple, that these approximations are these are approximations. Okay, these are not equal to. So if we want to take it, suppose there is variable v, which is equal to approximation of, so where v is approximation of u. Yeah, right. So I'll come to it. Minus vkn upon delta t equals to, why we have taken v, I'll just explain to you. Please wait. Okay, minus 2 vkn plus vk minus 1n upon delta x square. But now the question is, why we have taken v instead of u? Because everything we were doing in u, why suddenly v comes? Anyone from the audience? No? Okay. So no issue. So what we realized, that v is here approximation of u. Basically, you want to compute, right? But if you take a approximation of this ut, right? You want to take approximation of ut, so it is not equal to. Okay, it is not equal to. So we once you take it as a discrete variable, right? It is continuous one. I told you this one, this definition you see. It is continuous one. Ut equals to ux plus t plus delta t minus uxt upon delta t. But once you take its discrete approximation, it is better to take a new variable which is equal to ut. So we can simply write here, okay, let me write it clearly here. So then I think it would be clear that a reasonable approximation, or maybe in this way, maybe in not in this way, uh, Vn plus 1 k minus Vkn upon delta t is an approximation is an approximation of ut. Now I think it's clear, right? So Vkn plus 1 minus Vkn upon delta t is an approximation of ut. Okay. Now from this we are going to obtain the solution. Let me draw the grid, right? Let me draw the grid. So what will be our grid? This, 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 and this, right? And this we are going to understand perfectly that at what points we need to find the solution. What are the points where we will find the solution? At this point, at this point, at this point, then at this point, at this point, at this point, then at this point, at this point, at this point, and then at this point. Why? Because all this yellow color point, we know the solution here. Here also we know, here also we know, here also we know, here also we know, right? Here also we know, here also we know. Right. So all the yellow points, we know the solution. Why? Because of boundary conditions, right? And here because of initial conditions. So we all agree that we have divided the domain of our PD 0 to 1, 0 to 1 in total of uh, 12 point. I mean, although we divide it in 16 point, but at many points we don't need the solution, right? We don't need to find the solution. So we need to find the solution only at these 12 points. And how will we find? We will find using this equation. So till now what we understood that what is the procedure? The procedure is simple, that first we need to discretize the domain. We need to make a grid. After making the grid, we need to discretize the PDE. How do we discretize the PDE? We simply need to replace the derivatives by its discrete version. So time derivative, we put the discrete version of time derivative. The space derivative, we put the discrete version of space derivative. Please note one point. If you notice carefully, let me circle it, right? Here in time derivative, you see n plus 1 and n. And in space derivative, you are seeing k plus 1, k and k minus 1. N is fixed there. And here k is fixed. So please try to understand that in time, and n is representing your time. Please see here. N is representing what? Time. N is representing time. K is representing x. So k is what? K is this. This is x0. This is x1. This is x2. This is x3. This is x4. This is T0, this is right, T1, T2, T3, T4. This is K and this is N. Agree? So suppose I need to find the solution at this point. Let me take this color. Maybe at this point. No, it is again the same one. We take another color. Just a minute. Yeah, this one. Maybe, yeah, this one, right? So suppose I want to find this solution at this point. So what it would be? It would be U, K is what? 2 and T is what? 3. How many of you understood? Right? This is U32. Sharthak, Aditya, Pooja, Jay, everyone, I please ensure us so that I can also be comfortable that whatever we are doing, it's comfortable to you, right? So only thing is we need to keep in mind it's not that complicated, but I just wanted to make it crystal clear. So we understood the PD first. We understood what does it mean by initial and boundary condition. We understood that a grid, 10 by 10 grid. I took a large grid to just explain to you. And then I said that you take the discrete version of your random variable, because see, on computer you cannot do continuously, right? You have to be discrete. Then we defined the derivative with respect to time and with respect to x. See, we can derive these using Taylor series approximation, but since we don't have that much time, so we are not going into it. These star and double star you can find in any book using Taylor series approximations. Now we wrote, so let me define the steps, right? So first, what we did, we write discrete version of derivatives in the PD. Right, this is first thing. Second, what you need to do, maybe from figure, it is clear at what points solution is to be obtained. It's not like at every point we have to obtain. No initial and boundary conditions, right? At what point solution is to be obtained. Now the question is how. Okay, so here you have used k and n. What is the value of k and what is the value of n here? Can anyone tell? K again 0, 1, 2, because k is 0 here, right? K is 0, K is 1, K is 2, K is 3, K is 4. 1, 2, 3, 4. And what is N? Again, same. N is 0, N is 1, N is 2, N is 3, N is 4. Everyone comfortable? What is the value of K and N? Everyone, right? So we know the value of K, value of N. We have written the discrete version of derivatives involved in the PD. From figure, we know that we need to solve. Again, the same question if you ask that what if I want the solution at 0.55. So you have to take more number of grids. That's it. It's not very difficult. Okay, so we have to take more number of grid points in x direction. If you want solution time at 0.55, that means you have to take more number of grid points in time direction. Okay, now the question is how to find the solution u or v. Maybe v is approximation. See, please be clear, approximation means in layman language you can understand that whatever we are computing, it is not exact solution, it is an approximation to the exact solution. Numerical things cannot be exact, right? We all know. If you have read Taylor series expansion, you all know, right? Whenever we truncate Taylor series, it becomes like somewhere there must be some error. Agree? So the idea is simple, that why we are taking v, because our original equation is in u variable, and whatever we are going to get numerically, that is not u. That is not u, right? That is an approximation to u. And that's why we have taken that approximation as v. I hope now it's clear, right? That why we have taken v, because whatever we will do this numerically, we are not going to get u. We are going to get only the approximation of u. And that's why let us denote that by a separate variable, so that we should not get confused. Here we have denoted by u only. You see this exact solution. Why? Because here there is no approximation. It is exact solution. There is no error at all. Clear? So whenever we represent exact solution, we represent by the same variable. But whenever we do numerics, right, we find the solution by numerical method, we use a different notation just to ensure that yes, whatever you are computing, it is not exact. It is an approximation of you. But now the question is how good your approximation is. That is the question. That is different. Agree. So our question is how to find the solution v. Yes, this v, right? V. And v is what? Approximation of u. How to find this solution v at all these points. How many points are there? 12 points at all these points. I told. So now it will be clear that if you increase number of points, what the problem will come. Right. So now we have understood till here. I hope it is clear to each and everyone. I think we may take a break of 5 minutes, right? Because it's already 1 hour, right? So it will be good for you also. And we'll take a break of 5 minutes, and then we'll meet again after 5 minutes. Is that okay? Yeah. Thank you, everyone.